Somewhere over the middle of the Pacific in the winter of 1944, there was a paper balloon about 30 feet across, drifting east at maybe 150 miles an hour, with a small pile of explosives hanging underneath it. Nobody in America knew what was carrying it. They didn't know the thing existed. You've probably seen the phrase, "The jet stream is broken." It's on thumbnails, it's in headlines, it's in the title of this video, and most meteorologists don't love it. It isn't broken, it's doing something, and what it's been doing over America this year is unusual enough that people who watch this for a living have said so out loud. So tonight, the whole thing properly, what it is, who found it, and how badly that went. How you watch a river you can't see, what it's already done this year, what the models say about the next 6 months, and, my favourite bit, where the science quietly disagrees with itself. If you fancy more of this sort of thing, subscribing helps. That's the last you'll hear about it. Right. The object itself. The jet stream is a fast and narrow current of air that flows west to east and wraps all the way round the planet. That's it. That's the whole thing. It sits roughly 8 to 12 kilometers up, which is somewhere between 26 and 40,000 feet, depending on the season and where you're standing, and it separates cold air from warm air. Now, the first thing I have to get out of the way, because it comes up every single time, is that this is not the Gulf Stream. The Gulf Stream is water. It's an ocean current, it's in the Atlantic, it's the thing that keeps Britain weirdly mild for somewhere that sits at the same latitude as Labrador. The jet stream is air. Different fluid, different ocean, different everything. They just both have stream in the name, and both flow roughly the same direction, which apparently was enough to permanently confuse the entire English-speaking world. I've made peace with it. Mostly. So what makes it go? The engine is temperature contrast. That's the whole mechanism, and once you've got it, everything else in this video falls out of it naturally. Here's the bit that took me embarrassingly long to properly picture. Warm air is taller than cold air. Not lighter. Well, lighter too, but that's not the useful way to think about it. Taller. If you take a column of air and warm it, it expands upward. The same amount of stuff now occupies more vertical space. So imagine 2 columns of atmosphere sitting side by side. One's over the Arctic and it's cold, so it's squat. One's over Texas and it's warm, so it's stretched out tall. Now go up to about 10 kilometers and look sideways. You're near the top of the tall column and well above the top of the short one, which means the pressure at that height is higher on the warm side than the cold side. Air moves from high pressure to low pressure. Always. So up at that level, air starts sliding from the warm side toward the cold side. And that's where it would end if the planet held still. It doesn't. It's spinning, and that spin deflects anything that tries to move across it. In the northern hemisphere, everything gets nudged to the right of wherever it's headed. So that air trying to slide north gets bent, and bent, and bent, until it isn't going north anymore at all. It's going east. Parallel to the temperature boundary rather than across it. And once it's doing that, it just keeps doing it, all the way round the world. That's the jet stream. It's not a wind blowing from somewhere to somewhere. It's air trying to get from warm to cold, and getting permanently sidetracked by the fact that it's standing on a merry-go-round. The bigger the temperature difference, the steeper the pressure gradient, the faster it goes. Hold on to that sentence. It's going to matter a lot later, and I'm only saying it once. There's a detail here that most explanations skip, and it's the one that actually surprises people. There isn't one jet stream. There are 2 in each hemisphere. The polar jet is the famous one. That's the one sitting over the boundary between Arctic air and the milder stuff further south, somewhere over Canada and the northern United States most of the time, and it's the one that drives the weather people actually notice. Storms, cold snaps, the lot. Then there's the subtropical jet further south, higher up, generally weaker, formed by a completely different bit of machinery involving air rising near the equator, drifting poleward, and getting deflected the same way. It's the quieter sibling. Most of the time nobody talks about it. Most of the time. Keep that one in your back pocket too. We'll come back to it. And when we do, it'll be doing something genuinely strange. Now, the seasons. The jet is not a fixed thing on a map. It migrates. In winter, the Arctic is properly, viciously cold, while the mid-latitudes are only moderately cold, so the temperature contrast is enormous. Big contrast, strong jet. And it slides south, because the boundary between cold and warm air has slid south with it. In summer, the Arctic warms up. It's still colder than Florida, obviously, but the gap narrows a lot. Smaller contrast, weaker jet, and it retreats north. This is why, if you look at where tornadoes happen in America across a year, they walk. In spring, the activity spreads north and west, with the maxima moving into the Midwest and the Great Plains as the springtime jet pattern set up further north. By June, it's the Midwest and the central and northern plains, all because of their proximity to the late spring and early summer jet as it continues its retreat. By July, you're looking at the upper Midwest, the Great Lakes and the Northeast, the states nearest the Canadian border, purely because that's where the summertime jet has parked itself. Nobody plans this. There's no meteorological committee deciding that Oklahoma gets May and Minnesota gets July. It's just a boundary sliding north as the pole thaws, dragging its weather with it, and a whole continent's worth of severe weather climatology falling out of that one simple fact. I find that genuinely lovely, and I'm aware that says something about me. Right, and now the bit I actually think is the strangest thing about the whole phenomenon, and it's not the part anyone leads with. Everyone's impressed that it's fast, 200 miles an hour, that sort of thing. Fine, impressive. But hurricanes are fast too, and nobody's writing poetry about the pressure gradient. The strange bit is that it's narrow. This is a feature that circles an entire planet, 25,000 miles long, give or take, and it's a few hundred miles wide and a few kilometers deep. If you scaled the Earth down to the size of a football, the jet stream would be a thread wrapped around a ball, and that thread decides whether Chicago gets a blizzard. It's not a broad, gentle drift of air across the top half of the world. It's a filament, and the reason it's a filament is that same thing again. A rotating planet doesn't let air move sideways. It squeezes everything into these tight, fast, ribbon-like flows, because that's the only configuration that's stable when you're spinning. So when you hear that the jet stream shifted south, it isn't a vague regional smudge moving about. It's a thread that was over here and is now over there, and everything underneath it changed accordingly. And while we're here, the reason it sits at the height it sits at is worth a minute, because it explains why the number is what it is rather than something else. There's a ceiling above us. It's called the tropopause, and below it, in the troposphere, temperature drops as you climb, which is why mountains have snow on them and why the window on a plane is cold. Above it, in the stratosphere, that reverses and temperature starts going up again because of ozone-absorbing ultraviolet. That reversal is a lid, in the practical sense. Air that's rising can't easily punch through it, because once it gets there, it's colder than its surroundings and it stops going. So essentially all our weather, every cloud, every storm, all of it, is confined to that bottom layer, pressed up against a ceiling it can't get past. And the jet lives right up at that ceiling, because that's where the temperature contrast has finished accumulating. The pressure difference between the warm column and the cold column keeps building all the way up, so the wind keeps strengthening all the way up, and it peaks just before the lid. Here's the detail I like. The tropopause isn't at a constant height. It's higher over the tropics because warm air is taller, and lower over the poles, so it steps down as you go north, and it doesn't step down smoothly. It does it in a break, a sort of cliff in the sky, and the jet sits in the break, right in it. The reason it's narrow is partly that the boundary it lives on is narrow. The speeds, incidentally, are worth having straight. Typical is somewhere around 100 miles an hour, which is already faster than any surface wind most people will ever stand in. The maximum recorded is somewhere north of 250. And the ones over Japan in winter, the ones Oishi found and the B-29 crews met, are among the fiercest on Earth, which is a small piece of historical luck. The jet stream was discovered where it was discovered partly because that's where it's most obviously there to be discovered. And here's the thing that gets me. None of this was known 100 years ago. Not a bit of it. There was a continent-spanning, weather-controlling ribbon of air sitting 8 miles above every farm, every city, every person on the northern half of the planet, and we had absolutely no idea. Somebody had to find it. And the way that happened is, I think, one of the best and most frustrating stories in the history of science. Let's talk about Wasaburo Oishi. He was born in 1874 in Tosu, in Saga Prefecture, down in the southwest of Japan. He became a meteorologist at a point in history when being a meteorologist mostly meant looking at the sky and writing things down. And at some stage he got interested in the part of the atmosphere nobody could reach, which in the 1920s was essentially all of it above about 100 feet. He founded Japan's first upper air observatory, Tateno, northeast of Tokyo, and the method was about as simple as science gets. Fill a small balloon with hydrogen, Let it go and watch it through a theodolite until you lose it. Track the angles, do the trigonometry, and you can work out which way the wind was blowing at every height on the way up. Between March 1923 and February 1925, he did that 1,288 times. Sit with that number for a second. Nearly 1,300 launches. 2 years. Every one of them requiring somebody to fill a balloon, release it, follow it by eye through an instrument, record the readings, and then do the maths by hand. In winter, outdoors, on a hill northeast of Tokyo. The man watched balloons for 2 years, and what he found was that in winter, somewhere around 10 kilometers up near Mount Fuji, there was a belt of westerly wind moving at speeds that made no sense. Not a gusty day, not a fluke. A persistent, reliable, structural feature of the atmosphere over Japan that showed up season after season. He described it, in his own understated way, as a strong wind in the upper air. Some of his balloons ended up over the Pacific at a rate that frankly should have made someone somewhere sit up. A few reportedly made it as far as the United States. He had found the jet stream in the 1920s, with balloons and a telescope and an inhuman amount of patience, and then he published it in Esperanto. Now I want to handle this carefully, because the way this fact usually gets told is as a punchline, and I don't think it deserves that. Oishi was the board president of the Japanese Esperanto Institute. He held that role from 1930 to 1945, and he was, by all accounts, a true believer. And you have to understand what Esperanto meant to a certain kind of person in the 1920s. It had been constructed in the 1880s, deliberately, by a Polish eye doctor, as a neutral second language for the whole world, not to replace anyone's mother tongue, to sit alongside it. The idea was that if everyone had one shared language that belonged to no country, a lot of the misunderstanding that leads to people shooting at each other might simply evaporate. That's an idea a scientist in the 1920s could very reasonably fall in love with, especially a scientist in Japan, watching his own field conduct itself almost entirely in German and English, neither of which was his. Publishing in Esperanto wasn't eccentricity, it was a position. It was saying science should not belong to whoever won the last war. He wrote the first official report from the Aerological Observatory in 1926 in Esperanto, Rapporto de Aerologia Observatorio de Tatino, and in it he stratified his data by season and produced mean wind profiles, and the winter profile is the first known evidence of those persistent strong westerlies. Then he did it again, and again. 19 reports between 1926 and 1944, 1,246 pages, all of them in Esperanto. Smithsonian's Air and Space magazine put it about as gently as it can be put. The discovery may have been ignored partly because it arrived in a language few scientists in the field could easily read. 19 reports. Nobody came. I don't find that funny particularly. I find it a bit crushing. A man spends 2 decades doing careful, correct, world-altering work, deliberately publishing it in the language of universal human understanding, and the result is that literally nobody understands it. And here's where the story turns, and it turns in a direction he could not possibly have wanted. In April 1942, the Doolittle raid hit the Japanese home islands. 16 American bombers launched off a carrier, doing relatively little material damage and an enormous amount of psychological damage because the home islands were not supposed to be reachable. And the shock of that produced, among other things, a directive to the 9th Military Technical Research Institute to find some way of hitting back. What they came up with was balloons. The concept was that if you could get something to about 30,000 feet and let the wind have it, the wind would take it across the ocean. Which is a lovely idea and completely useless unless somebody can tell you whether it's actually true. So in late 1943, the army went and asked Hidetoshi Arakawa at the Central Meteorological Observatory in Tokyo, and Arakawa did what any sensible person would do. He went and got Oishi's data, 1,300 balloon launches, 20 years old, sitting there in Esperanto. Arakawa extrapolated the currents out across the Pacific and worked out that a balloon released in winter, holding an altitude between 30 and 35,000 feet, could reach North America in 30 to 100 hours. He also established that the strongest winds ran from November to March, at speeds approaching 200 miles an hour. He was right. All of it. Off the back of a man watching balloons through a telescope in 1924. So they built the things. Paper balloons, layers of washi glued with konjaku paste, made in enormous quantities by workers including a great many schoolgirls, most of whom were never told what they were making. an altitude control system underneath with ballast sandbags that dropped automatically when the balloon sank too low, and a valve that vented gas when it rose too high, so the thing could porpoise its way across 5,000 miles of ocean, holding roughly the right height for roughly the right amount of time. It's an astonishing piece of engineering. It is also, obviously, a weapon designed to start fires in a country full of people, and I'm not going to pretend that's neutral. It just isn't the part of the story I find most interesting. The part I find most interesting is what happened when they started arriving. Because they did arrive. Fragments turned up in Alaska, in Oregon, in Montana, in Kansas, one as far east as Michigan. And American investigators looked at them and reached a conclusion that tells you everything about how little anyone knew. They assumed submarines. That was the theory. Japanese submarines sitting off the west coast launching them from close range. Because the alternative, that these things had been launched from Japan and crossed the entire Pacific unpowered, was, in the words of the people looking at it, inconceivable. Nothing could travel that far. There was no mechanism. There was no known thing in the sky capable of doing that. There was, of course. It was right there. It had been documented in detail in print for 20 years, and the Japanese Navy had actually tried the submarine idea first anyway. But the current that made the balloons possible was, to American investigators, simply not a thing that existed. The other theory doing the rounds was that they'd been launched from German prisoner of war camps in the American interior, which is, I have to say, a real swing. Somebody in a room genuinely reasoned their way to "the prisoners are making balloons" before they reasoned their way to "the wind can do that." I think that's the quietest and strangest moment in this whole story. Not the weapon, the gap. An entire nation looking at physical, undeniable evidence of a continent-spanning atmospheric river and concluding reasonably that it must be submarines. And then, from the other direction, the Americans found it themselves, the hard way. By late 1944, B-29s were flying from the Mariana Islands up to Japan at altitudes nobody had bombed from before, 30,000 feet and above, which was the whole point of the aircraft. And they started running into winds that broke their arithmetic. Crews on flights up from the Marianas reported westerlies of 160 to 200 knots. On the 24th of November 1944, a squadron on the run from Kyoto to Tokyo hit a tailwind of 140 knots. 140 knots of tailwind means you're arriving whether you like it or not. Ground speed goes silly, the bombing computer's assumptions collapse, and the bombs, which are at the end of the day just objects dropped into a moving fluid, go somewhere else entirely. Fuel calculations for the return leg into that same wind stopped working in a way that got people killed. Similar things had been reported over Europe. 103 meters per second at 25,000 feet over central Germany in early 1945. Photographic reconnaissance flights between 1942 and 1945 running into strong winds at 28 to 35,000 feet. The reports existed. They were largely disregarded because a lone pilot saying the wind was doing something impossible is a lone pilot who has misread an instrument. Then enough of them said it. And in 1947 the thing finally got a name and a proper description in a paper published under the collective byline Staff Members out of the Department of Meteorology at the University of Chicago, alongside work by Carl Gustav Rossby, whose name is going to come up again shortly. That's the moment it entered the scientific literature in a language people read, although even then the picture was incomplete in a way I find quite endearing. Reading those early papers back, you can see them working out that the jet is tied to the boundary above the polar front, stretching up to the top of the weather layer. They got that right almost immediately. What they hadn't fully appreciated yet was the hemispheric bit. That it was one thing. That it went all the way round, meandering, as a single connected object. They'd found the local phenomenon. It took a while to realise the local phenomenon was global. And there's a small linguistic detail I like here. The name itself, jet stream, comes from the German Strahlströmung, jet current. It was in use in German meteorology before the war, which means the phrase and the phenomenon were both floating around Europe and Asia for years, while the English-speaking world got on with not knowing about either. 3 separate groups, on 3 continents, in 3 languages, all with a piece of it, and it took a world war and about 25 years for anyone to put the pieces on the same table. Oishi died in 1950. He got the Order of the Sacred Treasure. He's listed now as the man known for the jet stream, and I'm glad about that. but I'd love to know what he made of those last few years, watching the field finally arrive at the thing he'd been describing for 2 decades, in the wrong language, to nobody. Anyway, since we're on the subject of how nobody could see it, we can see it perfectly well now, and the way we do that is much less exotic than you'd think. A latex balloon and a foam box. That's it. That's the front line of atmospheric observation in 2026. Not a satellite, not a supercomputer. A balloon about the size of a beach ball when it leaves the ground, and a little white polystyrene box on a string underneath it, roughly the weight of a small apple. The box is called a radiosonde. It's got a thermometer, a humidity sensor, a pressure sensor, a GPS chip and a small radio transmitter, and it costs a couple of £100, and it is thrown away every single time. Here's the part that I think is quietly extraordinary and almost never gets mentioned. They go up twice a day, fine, but they go up twice a day at the same moment, everywhere, simultaneously, across the entire planet, at 00 and 12 Zulu, which is to say midnight and midday Greenwich time, regardless of where you actually are. So at midday in London, it's early morning in Denver, and evening in Tokyo, and it does not matter. Somebody in all 3 places is walking outside with a balloon. Roughly 900 stations worldwide, every 12 hours, coordinated since the middle of the last century. There's something about that I find genuinely moving, and I've thought about why. I think it's that it's the least glamorous international cooperation imaginable. There's no summit, there's no signing ceremony, there's a bloke in Nebraska, and a woman in Norway, and someone at a station in the Antarctic, all walking out into whatever weather is happening to them personally at that exact second, letting go of a balloon and going back inside. And it has just kept happening for 70-odd years, through everything. No notes, genuinely. So the balloon goes up, and as it climbs, it's radioing back temperature, humidity and pressure, and the GPS is tracking where it is, which is how you get the wind. You don't measure wind directly. You measure where the balloon has drifted to and how fast, because the balloon isn't fighting the air, it's part of it. The balloon is the wind. It's the same trick Oishi was doing with a telescope, just with the maths handled automatically and the results arriving instantly instead of being worked out by hand afterwards. It rises for about 2 hours. The air pressure outside keeps dropping, so the balloon keeps expanding. That beach ball becomes something the size of a small house by the time it's up around 100,000 feet. And eventually the latex simply can't stretch any further and it bursts. Then the box falls. There's a small parachute, mostly so it doesn't hurt anyone on the way down, and then it lands somewhere. A field, a wood. The sea, quite often, because a lot of the planet is sea. Most of them are never recovered. There's usually a little printed note asking whoever finds it to post it back, and some people do, and it's always slightly charming when they do, but the honest position is that the overwhelming majority of radiosondes ever launched are simply lying about in the landscape, having done their one job perfectly and then been forgotten. Which is a fairly good deal, all things considered. Now, that's the backbone, but it's not the whole picture. Satellites fill in everything between the stations, which is most of the world, because balloon stations are on land and land is the minority. They can't feel the air the way a sonde can, so they infer. They read radiation coming off the atmosphere at different wavelengths, and different wavelengths come from different heights, so you work backwards to a temperature profile. They also track cloud and water vapour motion between successive images, which gives you wind, sort of, at whatever level the cloud happens to be. That inference step is doing a lot of heavy lifting, and it's worth being honest about its limits. A satellite reading a temperature profile isn't measuring the temperature at a height, it's measuring a weighted average over a fairly thick slab of atmosphere, and then unpicking that into levels using assumptions. It's very good. It is not the same as sticking a thermometer in the air, and forecasters know exactly which one they'd rather have, which is why the balloons persist, in an era where that seems faintly absurd. There have been serious conversations for decades about whether the radiosonde network is worth what it costs, and the answer keeps coming back yes, because everything else in the system is calibrated against it. The balloon is the ground truth. The satellite is the coverage. Take the truth away, and you've got beautiful global coverage of numbers nobody can check. And then there's the fleet. Thousands of commercial aircraft, All day, every day, quietly reporting temperature and wind from wherever they happen to be. Airliners cruise at exactly the altitudes we care about, because of course they do. That's the whole reason they're up there, chasing the tailwind or dodging the headwind. Every transatlantic flight is, incidentally, an instrument reading. So you've got balloons, satellites, and aeroplanes, all producing numbers in different formats, at different times, from different places, with different error characteristics. And then comes the step that nobody outside forecasting has ever heard of, which is genuinely the hard part. It's called data assimilation, which is a terrible name for something quite clever. The problem is this: to run a weather model, you need to know the state of the entire atmosphere right now, every point on a three-dimensional grid covering the whole planet, and you don't have that. You have a scattered, patchy, uneven mess of observations, some of which contradict each other. So what the model actually does is start from its own forecast, the one it made 6 hours ago for right now, and then use the observations to nudge that forecast toward reality. Not replace it, nudge it. The prior guess and the new evidence get weighted against each other based on how much you trust each one, and what comes out is the best available estimate of the current state of the sky, which means every forecast is built on the corrected corpse of the previous forecast, forever. It never starts from scratch. There is no clean slate. I love that. It's such an unglamorous, deeply practical piece of engineering, and it's doing more work than any other single component of modern weather prediction. Before we get to what they look for, a word about what they're actually looking at, because it's not a video of the sky. The jet on a forecaster's screen is a chart. Specifically, it's usually the 250 millibar level, which is a pressure surface, not a fixed height, but the altitude at which the pressure has dropped to 250 millibars, which works out around 34,000 feet, give or take, depending on how warm the air below it is. Meteorologists use pressure as a vertical coordinate rather than height, which sounds mad until you realize the air itself doesn't care about meters, it cares about pressure, so you may as well use the units the atmosphere is actually working in. On that chart, the jet shows up as bands of color where the wind speeds pile up, and within it you get jet streaks, localized patches where the flow accelerates hard, sometimes doubling the speed either side of it. Those streaks matter enormously, because air entering one has to speed up, and air leaving one has to slow down, and that acceleration forces air to converge and diverge at different points around the streak, which pulls air up from below at some corners and pushes it down at others. Which is how a thing 8 miles up reaches down and makes it rain. Not by raining, by tugging. And here's the part everyone's experienced personally without thinking about it. Airlines have known about this longer than the science has had a name for it, and they use it every single day. Flying east across the Atlantic, you ride it. New York to London can come in under 6 hours with a good tailwind. Flying back, you have to avoid it, which is why the return leg routinely takes an hour longer, and why westbound routes sometimes look bizarre on the map, tracking up over Greenland to get out of the way. Every time you've sat on a plane wondering why the way home takes longer, that's this. You've been paying a tax to Oishi's wind. Right. So what do they actually look at when they look at the jet? 3 things. Position, where the thread is, speed, how fast it's going, and waviness, which is exactly what it sounds like, and which is the one that tells you what your week looks like. The rule of thumb goes like this, and it's the most useful sentence in this entire video. A jet running fast and relatively flat means changeable weather. Things pass through, a front arrives, it rains, it clears, something else arrives. Nothing sits still because the jet is efficiently shoveling systems along and out the other side. Annoying, but survivable. A jet running slow and deeply looping means whatever is currently underneath you is staying. That's it. That's the diagnostic. Forecasters see a deep, sluggish loop develop, and they know that whatever's sitting in it, heat, cold, rain, nothing at all, has just been handed a lease. Which brings me to the thing I think is most misunderstood about all of this. People assume that because we can see the atmosphere in this much detail, we should be able to predict it. We've got the balloons, the satellites, the planes, the supercomputers. Surely you just run it forward. And the gap between we can see it perfectly and we can predict it is, I'd argue, the single most misunderstood thing in weather. Because the atmosphere is chaotic in the technical sense. Tiny differences in the starting conditions grow, not linearly, exponentially. A rounding error somewhere over the Pacific today is a completely different Thursday over Ohio in 10 days, and you cannot fix this by measuring better because you'd need infinite precision, and there's no such thing. So what forecasters do instead is run the model many times, from slightly different starting points, all of them equally plausible given what we actually know. That's an ensemble. And if all 50 runs agree, you've got a confident forecast. If they scatter, you don't, and no amount of computing power is going to save you. There's a number attached to this, and it's been stubbornly hard to move. The useful limit for a deterministic forecast, this weather, this place, this day, sits somewhere around a fortnight. Beyond that, you're not forecasting weather anymore. You're describing climate, which is a statement about the distribution rather than about Thursday. And the frustrating part is that the ceiling isn't about computing. You could have a computer the size of the moon, and it wouldn't help, because the limit lives in the physics, not the hardware. Forecasts have got dramatically better over the last 40 years. A 5-day forecast now is about as good as a 3-day forecast was in the 80s, which is a genuinely staggering improvement nobody ever credits. But the wall at the end hasn't moved much, and probably won't. This is why seasonal forecasting stays hard even when the signal looks enormous. You can know with real confidence that the deck is stacked a certain way. You cannot know what card comes off the top, and that's a distinction I want to plant here and lean on later, because it's going to matter a great deal when we get to what the models are saying about this winter. Even very strong background signals do not automatically deliver very strong regional outcomes. The signal changes the odds. It doesn't write the story. I've got a whole thing planned about how ensembles actually work under the bonnet, because it's a genuinely lovely bit of maths, and it deserves its own video rather than 4 minutes here. For now we've got a thread, we can see it, and we know that when it loops, things stop moving. So let's talk about the loops. A lid on a pot. That's the image, and it's not mine. It's the one meteorologists reach for, and it's good enough that I've never found a better one. When a heat dome sets up over somewhere, the thing sitting over the top of it works like a lid on a pot. The heat can't get out, the steam can't escape, whatever's underneath just keeps cooking. Everything in this section is downstream of that picture. Let's work outward from it. So, why is the jet wavy at all? It doesn't have to be. You could imagine a version of this planet where the thread just runs around the world in a neat circle, tidy as a hoop. That version doesn't exist, and the reason is a man called Carl Gustav Rossby, or rather the maths he did. Quick word on him, because he keeps turning up and he's earned it. Swedish, trained under the Bergen School in Norway, which was the place in the world for atmospheric physics in the 20s. Ended up in America. Ended up running the department at Chicago, which is where that 1947 paper came from. And his particular gift was being willing to throw away detail. He'd take the atmosphere, an object of absolutely unbounded complexity, and say, right, ignore nearly all of that. What's the simplest thing that could produce the behaviour we're seeing? That's a rarer skill than it sounds. Most people, handed a complicated system, try to include more. Rossby kept taking things out until the thing that was left explained the sky. Rossby waves work like this. Take a parcel of air moving along in that fast current. It's got a certain amount of spin, partly its own, partly the planet's, and the planet's contribution depends on latitude. Near the pole, you're sitting almost flat on the axis of rotation, so you inherit loads of it. Near the equator, you're side on, so you inherit almost none. Now nudge that parcel north. It's picked up more planetary spin than it wants, and to balance the books, it has to spin the other way itself, which curves it back south, so it heads south. And now it's got too little, so it corrects the other way and curves back north. Overshoot correct forever. That's a Rossby wave. It's not turbulence and it's not chaos. It's a restoring force, exactly like a plucked string, and the string in this case is a current of air 10 kilometers above Nebraska. A fast fluid on a rotating sphere doesn't have the option of going straight. Waviness isn't a malfunction, it's the resting state, which is worth saying clearly because the jet stream is wavy is not, by itself, news. It's always wavy. The question is only ever how wavy, and how fast the waves are moving along, and that second part is the one that matters. Normally the waves travel. The whole pattern shuffles east, so a ridge sits over you for a day, and then it's over the next place, and the trough behind it arrives, and you get weather. Plural. Different weather, one after another. Sometimes the waves stop moving, that's blocking. Here's the mechanism. You get a big ridge, a poleward bulge in the flow, with high pressure underneath it, And if that ridge gets amplified enough, it stops behaving like a bump in a moving stream and starts behaving like an obstacle in it. The flow can't push through, so it goes round. And once it's going round, it's reinforcing the thing it's going round, and now you've got a self-sustaining structure sitting in the middle of the sky refusing to leave. That's the blocking high. That's the upper level ridge. That's the lid. If it's stable, it can last days or weeks. And underneath it, air is sinking, and sinking air warms as it compresses, and clear skies mean the sun's doing its worst, and the ground dries out, and dry ground can't cool itself by evaporating anything, so it just heats further, which strengthens the ridge above it. Everything feeds everything, that's what a heat dome is. Not weather that's hot, weather that's stuck, plus time. And this next bit is the important one, I think, and it's the reason I'd rather people understood blocking than understood almost anything else in this subject. Blocking is symmetrical in its cruelty. The exact same mechanism that heat traps cold. The loops trap cold air when they dip southward, and warm air when they surge northward, and they can equally confine dry air, or park a low-pressure system in place so it rains on the same valley for a fortnight. It has no preference, it's just a stuck pattern. Whether that ruins your summer or ruins your winter is purely a question of which way the loop happened to bend and where you happen to be standing. And there's a thing people find counterintuitive here that I want to head off because it comes up every time. A big cold outbreak is not evidence against a warming planet, it's frequently evidence of the same machinery. Cold air has to be somewhere. The Arctic doesn't stop making it. So if a deep trough digs south over Texas, the cold that's now in Texas has left somewhere, and that somewhere is running unusually mild while everyone in Texas is having a very bad week and drawing conclusions about the climate from their driveway. The pattern isn't creating cold, it's relocating it. And relocating cold to a place that isn't built for it is, weirdly, one of the more expensive things the atmosphere can do, because places that get cold every year are ready for it and places that don't aren't. So when somebody tells you a blocked jet stream means heat, no, it means persistence. The heat is a detail. There are shapes to it as well, and forecasters name them, which I enjoy far more than I should. There's the omega block, which is called that because on a chart it looks like a capital omega, the Greek letter, the horseshoe. A big ridge in the middle with a low pressure system sitting on either flank, and the flow arching up and over the top of the whole arrangement. If you're under the arch, you're getting sun and heat for as long as it lasts. If you're in one of the lows on the shoulders, you're getting rained on for exactly the same duration, which is a fairly brutal bit of geographic luck. And there's the cut-off low, which is a beautiful little bit of atmospheric mischief. A trough digs south, and digs, and eventually the bottom of it pinches off entirely from the main flow, like a bubble breaking off a stream of water. And now you've got a self-contained cold low sitting there, completely detached, with nothing to steer it, because the thing that would normally steer it is now going past overhead and paying it no attention whatsoever. Cut-off lows are notoriously bad in models. They wobble, they wander, they sit still for 4 days and then dart off in a direction nobody predicted, because the flow they're embedded in is too weak to make them do anything in particular. Forecasters call the general problem low predictability, which I think is a very polite phrase for this thing does whatever it likes. Then there's the third thing, which is split flow. Instead of one thread, you get two. The current divides, one branch curving north, one diving south, and the gap between them has nothing steering along a single path anymore. Systems that would normally get picked up and moved along don't get picked up. They wander into the gap and mill about. Split flow tends to make forecasters miserable because the two branches interact, and things dropped by one can get caught by the other days later, in a way that models genuinely struggle with. It's the atmospheric equivalent of a junction where nobody's got right of way, right? I want to plant two things in the ground here, because there's a version of this subject that treats all of it as brand new, and it isn't. 2018, Europe. That summer produced record temperatures and wildfires across a huge chunk of the continent, and the cause, in part, was a jet stream weaker than usual, which let hot, high-pressure air linger in the same place instead of being moved along, same mechanism, same lid, 8 years ago, and go further back. 1980, the United States. A strong ridge set up over the Midwest and the Southern Plains in June, and simply stayed. It was among the most destructive and deadliest natural disasters in American history. At least 1,700 people died. Agricultural damage hit $20 billion, which is somewhere around $76 billion in modern money, and it sits on NOAA's list of billion-dollar weather disasters to this day. 1980. Before most of the modern conversation existed, before the satellites we use now were up, a blocking pattern parked over America and killed 1,700 people, and the physics of it was exactly what I've just described. I'm not raising that to be contrarian, and I'm certainly not raising it to suggest nothing's changed. I'm raising it because I think the honest version of this subject is more interesting than the version where everything is unprecedented. Blocking is old. Rossby described the machinery in the 40s. Jerome Namias was writing papers dissecting the anatomy of Great Plains' protracted heat waves in 1982, using 1980 as his case study, and if you read them, they're describing something we'd recognize instantly. The interesting questions are about frequency and duration, and whether the pattern is changing. Not about whether the mechanism is new. It isn't. It's the oldest thing in the room, and that's most of the vocabulary. Waves, because a spinning planet doesn't do straight lines. Blocking, when the waves stop travelling and something sits. Split flow, when the thread comes apart into two. Everything America has been through this year is some combination of those three words, which is where I want to go next, because 2026 has been a genuinely odd year, and not always in the direction you'd expect. Let's go through the year. Not building to anything, just walking through it, month by month, because the shape of it is interesting on its own. February, the stratosphere. There's a thing above the jet stream that most people never think about, which is the polar vortex, a big cold cyclone that spins over the Arctic in winter, well up in the stratosphere, and when it's strong and tidy it more or less pins the cold air in place. When it gets disrupted, the cold can spill, and in mid-February a sudden stratospheric warming event was confirmed, and it heavily destabilized the vortex. Normally that's a fairly reliable signal. The vortex gets clobbered, the disruption works its way down over a few weeks, and you get an Arctic outbreak somewhere in the mid-latitudes. That's the textbook. What happened instead is the bit I like. The downward influence ran into a counterforce. There was a Madden-Julian oscillation event going on. That's a big pulse of tropical convection that walks slowly east around the equator over a month or two, and it has a habit of reaching up and rearranging patterns thousands of miles away. And the two things met in the middle and interfered with each other. The result was that the vortex core got shoved out into the eastern hemisphere, and instead of Arctic air pouring into America, a high-pressure anomaly built over North America in the lower stratosphere, which promoted above-normal temperatures across the central and eastern US, while the cold built over western Canada instead. The early forecast didn't show that. They'd assumed the stratospheric signal would win, and it didn't, because of pressure interference from below tied to an anomaly sitting in the North Pacific. So, a textbook cold signal, comprehensively outvoted. That's the atmosphere for you. Two things that both work fine on their own, arriving at once, producing a third thing nobody ordered. And the aftermath rumbled on. By early March, the warming was properly underway, and forecasts at that point showed a vortex core finally set to descend and bring unseasonably cold air into the eastern United States and eastern Canada the following week. So the cold did arrive, weeks late, in a different place, at reduced strength, having been pushed around by a tropical wave over the Indian Ocean, which tells you something about the honest state of this. Not that the forecasters were wrong. The mechanism they identified was real, and it did what they said it would do. It just got outvoted, and then it didn't, and the whole thing played out on a schedule nobody could have written in advance. I find that reassuring, oddly. It's not that we don't understand the atmosphere, it's that the atmosphere runs several arguments at once and doesn't announce the winner. March the 16th. This is the day. If you want one date that explains why people started using the word broken, it's this one. And the thing I want you to notice is that it isn't one extreme, it's all of them. On the same day, in the same country, a blizzard dumping snow by the feet around the Great Lakes, damaging high winds with tornado threats inside them, marching across the eastern half of the country, followed in behind by Arctic cold. An unprecedented heat wave building across the southwest, more than 2 feet of rain falling in Hawaii, drought sitting across more than half the nation, and a large fire burning in Nebraska, with more expected across the west. All of it, one Monday. The framing meteorologists used at the time was the normal seasonal clash of cold and warm air colliding with a jet stream gone crazy, with a possible dash of climate change in the mix. And the southwest bit is worth pausing on because the numbers are silly. Phoenix has hit 100 degrees in March exactly once in its recorded history. It doesn't normally start seeing triple digits until May. The forecast that week was for 5 consecutive days flirting with 107 or higher. The hottest March day in United States history is 108, set in Rio Grande City, Texas in 1954, and there was a real chance of that going. And then there's the line that made this whole thing travel. One Weather Service forecaster, writing up a routine forecast discussion, which is an internal technical document, not a press release, just a bloke typing notes for other meteorologists, typed the words, "I audibly gasped" when he looked at the temperatures coming out of the model. That's it. That's the alarm. That's the whole "forecasters are genuinely alarmed" thing, and I love that it's this because it's so much better than a press conference. It's a professional at a desk, looking at a number and briefly forgetting to be professional. Jeff Masters, over at Yale Climate Connections, said at the time it'd be the kind of unusual event that gets studied for years to come, the way the 2021 Pacific Northwest heat wave has been. And on the heat specifically, he was blunt, that this was the type of extreme heat you could not get without human-caused climate change. I'll flag that's an attribution, not my claim. He's a serious person, and it's a serious statement, and I'll come back to why the attribution matters later. May. And here's my favourite thing about this year, because it goes the wrong way. May is supposed to be the big one. Peak tornado season, the plains, the whole thing. May 2026 was extremely below average. 106 confirmed tornadoes in the month. Only 3 rated EF2 or above. Only 2 hit EF3 or above. Why? The transition. The ocean was in the middle of switching from La Niña to El Niño, and that transition suppressed severe weather. The subtropical jet was weak, which meant there wasn't much wind energy up top to make thunderstorms rotate, and a thunderstorm that can't rotate doesn't produce much. Meanwhile, the northern branch of the jet stayed up in Canada rather than coming down to play. Add persistent troughing over the eastern states and severe drought across the high plains, and you get cool, dry air spreading across the middle of the country for most of the month, with nothing like enough energy for a real outbreak. So there's your subtropical jet doing something. Told you it had come back. And I think this is genuinely important because it cuts against the whole shape of how this subject gets sold. A disrupted jet stream configuration produced one of the quietest Mays in recent memory. Not a catastrophe, an absence. Thousands of people in Oklahoma and Kansas had a nice spring, and the reason was the same machinery that everyone's shouting about. Pretty wild, honestly. Nobody makes a thumbnail out of "not much happened in Kansas," and it's a useful corrective for a habit I think we've all picked up, which is treating every unusual atmospheric configuration as automatically bad. It isn't. It's just unusual. Sometimes an unusual configuration means 106 tornadoes instead of 200 and something, and a lot of people got a spring where nothing happened to their house. That's a real outcome. It's just not one anyone's counting because we only count the bad ones, and a thing that didn't happen leaves no evidence at all. Late June into July, the dome. And here the lid came down properly. Records tied or broken across major cities in both the United States and Canada. Atlantic City, New Jersey, hit 106 on the 4th of July, which was the peak. In Canada, the heat drove big thunderstorms on Canada Day itself, the first, which caused widespread flooding and left thousands of homes without power. In the States, the conditions strained public services across the board. Public transit delays, the grid under pressure, hundreds of thousands of homes without power, which is the part that actually gets people, and I'll come back to it. And the timing on this one was almost comically bad, because it landed on the World Cup. There were heat warnings up for East Coast venues heading into the tournament, players and crowds in the middle of the afternoon under a lid, which is one of those moments where the abstraction stops being abstract, because a heat dome over the eastern seaboard is a meteorological pattern, right up until the point where it's 90,000 people in a stadium. In Canada, Ontario and Quebec were both under heat warnings as the thing spread north, which is not a sentence anyone particularly wants to write about early July, and the pattern kept going. The Billings reading came on the 12th, more than a week after the Atlantic City peak, 3 states and 1,800 miles away. That's the thing about a stuck ridge. It doesn't necessarily stay perfectly still. It shuffles, it reorganizes. It hands the worst of itself to somewhere new while staying fundamentally the same feature. There's a lovely records-keeping wrinkle in this one too. On the 12th of July, Billings, Montana recorded 111 degrees, and both the National Weather Service and ABC called it an all-time record for the city. Which is odd, because Billings recorded 112 on the 31st of July 1901. That's not a conspiracy. It's the deeply unglamorous reality of historical climate records. Station moves, instrument changes, sighting differences, different observation practices. Sometimes an old reading exists but isn't considered comparable to a modern one, and the official record starts from wherever the modern series begins. It happens constantly, it's usually defensible, and it drives people who like tidy numbers absolutely round the bend, me included a bit. But there you go. One more thing about that March day, because there's a detail in it I skipped and it's the one I keep thinking about. Hawaii. More than 2 feet of rain. 60 centimetres. Hawaii is not a place that struggles with the concept of rain. Parts of it are among the wettest inhabited spots on the planet. But 2 feet in a stretch is a different category of thing, and the reason it's in the list at all is that it demonstrates the point about split flow better than anything else that week. A moisture plume that had nothing steering it, arriving somewhere it stayed, doing what unsteered moisture does when it stops moving. Blizzard in Michigan, tornado threat in Ohio, 107 in Phoenix, 2 feet of rain in Honolulu, fire in Nebraska, one country, one day. That's not 5 events. That's one event wearing 5 costumes, and underneath all of it, the drought. 61% of the lower 48 in moderate drought or worse. 45 states. That's the canvas everything else in this year has been painted onto, and it's not a headline because it's slow. Nobody films a drought. It just sits there being 61%. But it's the thing that makes the heat worse, because dry ground can't sweat. And it's the thing that makes the fires possible. And it's the thing that a wet spring might have fixed and didn't. So that's 2026 so far. A stratospheric warming that got outvoted, one Monday in March that did everything at once, a May that was suspiciously quiet for exactly the same reasons, a July that broke 100 cities, and drought underneath all of it the whole time. And the reason for a fair chunk of that is sitting in the Pacific Ocean. Water, not air for a bit. There is a patch of ocean along the equator in the Pacific, roughly between Ecuador and the middle of nowhere, and its temperature is arguably the single most consequential number in seasonal forecasting on Earth. Not because that water matters to anyone directly, nobody lives there, but because of what it does to the sky above it. Here's the machinery. Normally the trade winds blow east to west along the equator. They've been doing it forever, and because they've been pushing on the surface of the Pacific for the whole of geological history, they physically piled the water up on the western side. Sea level near Indonesia sits noticeably higher than sea level near Peru. We're talking tens of centimetres of permanent wind-driven tilt on an entire ocean. I do like that, as a fact. There is a permanent slope on the Pacific Ocean, put there by wind, and it has been there longer than we have. That warm water piles up in the west, and warm water evaporates, and evaporation feeds thunderstorms, so the western Pacific is where the atmosphere does most of its rising. Meanwhile, in the east, because the surface water keeps getting dragged away, cold water wells up from below to replace it. Cold water doesn't do thunderstorms, so the eastern Pacific sits there, cool and comparatively quiet. So, warm and stormy in the west, cool and calm in the east. That's the resting state. El Niño is what happens when the trades slacken off, stop pushing, and the piled up water sloshes back east. The upwelling weakens because there's nothing dragging the surface away anymore. The cold tongue in the east warms up, and now the whole engine has moved. The thunderstorms that were sitting over Indonesia relocate thousands of miles east into the central Pacific, and that's the bit that matters to America. Because the atmosphere is a connected system, and if you pick up the biggest heat source in the tropics and move it several thousand miles, everything downstream reorganizes around the new position. That's a teleconnection. It's not spooky. It's just a very large thing moving and the rest of the sky rearranging itself to cope. Since we're on the subject, the discovery of this is nearly as good a story as Oishi's, and much less tragic. The circulation involved is called the Walker circulation, after Gilbert Walker, who was a British mathematician sent out to India in 1904 to run the meteorological department there. And the reason he was sent was the monsoon. The monsoon failing meant famine, on a scale that's difficult to convey, and the Imperial administration wanted someone to predict it. Walker had no idea how. So he did the only thing available to a mathematician with no theory and a lot of clerks. He correlated everything against everything. Pressure at this station against rainfall at that one. Every combination. For years. By hand. And what fell out was a seesaw. Pressure in the Eastern Pacific and pressure in the Western Pacific moved in opposite directions, reliably, over enormous distances. When one went up, the other went down. He called it the Southern Oscillation, and he could not explain it, and he said so, and people thought he'd found a coincidence in a haystack of numbers. It took until the 60s for Jacob Bjerknes to work out that Walker's pressure seesaw and the Peruvian fishermen's warm water years, the thing they'd been calling El Niño for generations because it showed up around Christmas, were the same phenomenon seen from two different angles. Ocean and atmosphere, coupled, feeding each other. Two men, 50 years apart, one looking at the water and one looking at the air, describing one thing. Fun detail, Walker's other contribution to human knowledge is that he wrote a paper on the aerodynamics of the boomerang. Same brain, same period, he was just interested in things that curve. Now, 2026. On the 11th of June, NOAA's National Weather Service announced that El Niño had developed in the tropical Pacific and issued an El Niño advisory. That's an upgrade from watch. Watch means it's coming, advisory means it's here. Conditions are no longer forecast, they're present. The Niño 3.4 index at that point was sitting around plus 0.7 degrees and rising, with a strong subsurface warm pool underneath feeding continued warming. That subsurface bit is the tell, and it's the part I'd point at if you only wanted one thing to watch. The warm water doesn't arrive at the surface from nowhere. It's already there, 30 or 40 metres down, sliding east, waiting. When forecasters see a big subsurface anomaly, they're not really forecasting at all. They're reading something that's already happened and hasn't surfaced yet. Forecasters put the chance of sea surface temperatures exceeding 2 degrees at 63%. 2 degrees is the threshold where NOAA calls it a very strong event. And it kept escalating. By the 9th of July update, the Climate Prediction Center gave El Niño a 97% chance of persisting through early spring 2027 and an 81% chance of reaching very strong intensity between October and December. If that verifies, it'd rank among the largest events observed since modern records began in 1950. GFDL's July model runs, that's the Geophysical Fluid Dynamics Laboratory running their SPEAR system, indicate continued intensification of a very strong event through the autumn, peaking in late autumn or early winter. So that's where we are. It's here, it's growing, and the models think it's got a way to go yet. What does that do to the jet? In a typical El Niño winter, the North Pacific jet shifts south. That's the headline. And it brings the storm track over the southern tier of the United States, so the south gets wetter and stormier than it should be. The flip side is that the southward shift drags the track away from other places, which means drier conditions over the northern Rockies and the Ohio and Tennessee valleys. And on temperature, El Niño often leads to a warmer than usual winter across the northern US. The subtropical jet strengthens and shifts south, pulling more storms across the southern states, which if you were paying attention a section ago is the same character that was too weak in May to spin up tornadoes. Same jet, opposite complaint 6 months apart. I enjoy that more than I should. The quiet sibling gets a bad review in spring for not showing up, and then spends the winter being blamed for everything, and the mechanism for that is worth a sentence, because teleconnection can sound like hand-waving otherwise. Those relocated thunderstorms are pumping enormous quantities of air upward into the upper troposphere over the central Pacific. That air has to go somewhere, so it spreads out at altitude, and the spreading creates a pressure anomaly, and that anomaly sets off a train of Rossby waves that propagates away from the tropics and northeast across the Pacific toward North America, which is the same wave physics from earlier, just being triggered from below rather than arising on its own. The tropics pluck the string, the mid-latitudes get the note, and where the ridges and troughs of that wave train happen to land determines which American states get a wet winter and which get a dry one. It's a chain of ordinary physical steps, all the way from a slackening trade wind to whether it snows in Denver, and there's nothing mystical in it at any point. which I find much more impressive than if it were mystical, personally. Mystical is easy. A dozen boring mechanisms in a row, each one doing something unremarkable, arriving at a snowfall 4,000 miles away. That's the good stuff. Now here's where I want to be careful, because this is exactly the point where this subject usually goes off a cliff. Ken Graham, who runs the National Weather Service, put it about as plainly as anyone could. Every El Niño is not the same. Each one is unique, with its own imprint on our weather, and the Climate Prediction Centre's own language in their diagnostic discussion is even better, because it's more precise. Stronger El Niño events do not ensure strong impacts. They can only make certain impacts more likely. Read that again, because it's the sentence the entire second half of this video hangs on. They can only make certain impacts more likely. That's a forecasting body in a public document telling you the limits of what they know. And I think that's admirable, and I also think it's roughly the opposite of how this gets repackaged everywhere else. And if you want proof that the caveat is real rather than institutional throat clearing, here's my favourite example. 2023 was a La Niña year. La Niña is the other phase, cold water in the east, and it's supposed to bring dry conditions to the southwestern United States. That's the textbook. That's what water managers plan around. California had its 10th wettest year on record. Not slightly wetter, 10th wettest ever, in a year that was supposed to be dry. And the reason, according to research out of Scripps at UC San Diego, was atmospheric rivers. 9 of them, one after another, landfalling on California. And their finding wasn't that 2023 was a weird one-off. It was that atmospheric rivers explain the majority of a typical ENSO years. They can simply overwhelm the influence of El Niño and La Niña on annual precipitation totals across the American West, which is a genuinely awkward result if your job is water management, because you've built your seasonal planning on a signal that a handful of individual storms can just override. I think that's a bit brilliant, personally. The ocean loads the dice, and then a fortnight's worth of weather picks the dice up and throws them somewhere else entirely. And there's a structural reason forecasters were cagey about this one until relatively late, which has a wonderful name. It's called the Spring Predictability Barrier. The short version is that ENSO forecasts made in the spring are noticeably worse than forecasts made at any other time of year, and this isn't a software problem, it's the ocean. Spring is when the previous event has decayed, and the next one hasn't declared itself. The signal is smallest, the noise is proportionally largest, and a small nudge in March can be the difference between a strong El Niño and nothing at all by December. Forecasters have been running into this wall for as long as they've been making these forecasts. It's a known, named, permanent feature of the problem, and everyone has simply learned to live with it. Which is why the language shifted the way it did this year. In March, the statements were hedged, a transition to neutral, then El Niño likely to emerge, 62%. By May it was 82% for the summer. By June it wasn't a forecast anymore, it was an advisory, because it had already happened. That's not the models improving over 3 months. That's the ocean walking past the barrier and letting everyone see it. There's one more complication in 2026 specifically, and it's a good one. The Atlantic is unusually warm, and warm Atlantic sea surface temperatures favour storm development completely independently of what the Pacific is doing. Now, the textbook El Niño effect on Atlantic hurricanes is suppression. The stronger subtropical jet increases wind shear over the basin, and shear tears developing storms apart before they can organise. That's why NOAA predicted a below-normal Atlantic hurricane season this year. So you've got one signal saying quiet and another saying busy, and the outlooks are all trying to balance them, with the possibility that the basin lands closer to average than a typical strong El Niño year would suggest. And the disagreement is genuinely wide. The University of Arizona forecast 20 named storms, arguing the warm ocean will simply overpower the shear. Colorado State said 13, 20 versus 13. 2 serious institutions, same season, same data, and that gap is the story. And I'd rather have that than false agreement, honestly. A forecast everyone concurs on isn't necessarily a good forecast. It might just mean everyone's using the same assumption. That's not a failure of either group. That's an honest picture of 2 big physical signals pulling in opposite directions and nobody being able to tell you yet which one wins. Meanwhile, the eastern and central Pacific basins tend to get busier during El Niño, which raises tropical risk to Hawaii and pushes remnant moisture toward the desert southwest. Which, given that Hawaii already took more than 2 feet of rain in a day back in March, is a thing worth keeping half an eye on. So, the Pacific has loaded the dice. That much is established, it's official, and the probability numbers are high enough that arguing about it isn't interesting. What's interesting is whether the dice do what the loading says they should, and that's a question about the atmosphere's circulation, which is conveniently the exact thing the scientists have been arguing about for 14 years. I need to tell you something I don't know. This is the section where I'd normally deliver the mechanism, the neat, satisfying explanation for why the jet stream is behaving badly, tied off with a bow. And I can't, because the honest answer is that the field hasn't settled it, and I'd rather tell you that than pretend otherwise. But let's do the popular version first, and do it properly, because it deserves a fair hearing. It's not nonsense. It's a serious hypothesis from serious people. Here it is. The Arctic is warming faster than the rest of the planet. That part isn't in dispute at all. It's called Arctic amplification. It's driven substantially by sea ice retreat, and it's one of the most robustly observed things in climate science. White ice reflects sunlight. Dark water absorbs it. Take the ice away and you've swapped a mirror for a radiator, and the whole region warms at a rate the mid-latitudes don't come close to. Now go back to section 1 and that sentence I said I'd only say once. The engine is temperature contrast, bigger contrast, faster jet. So, if the Arctic warms and the mid-latitudes don't warm as much, the contrast shrinks, the engine weakens, and a weaker current is more easily pushed around. The waves grow, the flow meanders more, and things get stuck more often. That's the Francis and Vavros hypothesis. They published in 2012 with evidence linking Arctic amplification to extreme weather in the mid-latitudes, and again in 2015 with a paper whose title says it all, Evidence for a Wavier Jet Stream in Response to Rapid Arctic Warming. And it's elegant, that's the thing. It's a chain of dead simple physical steps, every one of which you can follow on your fingers, and it lands on a conclusion that explains everything anyone's worried about. It's on every explainer channel. It's in half the news coverage. It's in the reference material I read while putting this together, stated flatly, as fact. I've believed it myself for years without ever really interrogating it. Then in February 2020, Russell Blackport and James Screen published in Science Advances, and their finding in short is that Arctic warming does not drive a more meandering jet stream. Their opening framing is careful. Whether Arctic amplification has contributed to a wavier circulation and more frequent mid-latitude extremes, they say, remains an open question. Then they go at it two ways. They looked at climate model simulations, and they looked at the observed record going back 40 years. The model result is the awkward one. In simulations featuring strong Arctic amplification, where you crank the Arctic warming right up, exactly as the hypothesis requires, waviness remains largely unchanged. The models simply don't do the thing, and the observations tell an odd story too. For 2 or 3 decades from about the mid-80s, you had accelerated Arctic warming and a reduced temperature gradient, and it coincided with a wavier circulation. Which is why the hypothesis looked so good. It fit. But the trend toward a wavier circulation in autumn and winter reversed in recent years. Despite continued Arctic amplification, the Arctic kept warming, the waviness stopped increasing and went the other way, which leaves you with no long-term trend at all. Blackport put it about as fairly as you can. While there does appear to be a link between a wavier jet and Arctic warming in year-to-year and decade-to-decade variability, there has not been a long-term increase in waviness in response to the rapidly warming Arctic, and their proposed explanation is the part that really got me, because it's such a beautiful piece of scientific judo. They suggest the causation might run backwards, that the link is more likely a result of random fluctuations in the jet stream influencing Arctic temperatures, rather than the other way around. Think about what that means. A wavy jet drags warm air north into the Arctic, so the Arctic gets warmer, so you observe warm Arctic and wavy jet together, correlated beautifully for decades, and you conclude the warmth caused the waves, when actually the waves caused the warmth. That's the oldest trap in science, and it caught everybody, possibly including me, for the better part of a decade. Now, I want to be scrupulously fair here, because it would be very easy to tell this as popular idea debunked, and that's not what happened either. Francis didn't fold. She wrote a piece more or less asking why Arctic linkages to extreme weather are still up in the air, which is a fair question. Screen and Simmons had raised methodological concerns as far back as 2013. Barnes questioned the trend in 2013 too. Barnes and Polvani wrote about the lack of consensus. Kumu's group has argued for it from a different angle. Martineau, Vavros, Cohen, Overland, Stendhal, all of them, over years. The literature describes this as a decade-long debate that Francis and Vavris initiated, which is not an insult. Initiating a decade-long debate is roughly the highest compliment science can pay you. It means you asked a question that was worth 14 years of argument. There's a genuine methodological problem underneath all of it, which is that nobody entirely agrees on how to measure waviness. It's a wiggly line on a sphere. How wiggly is it? There isn't one obvious answer, and it turns out the observed positive trend beginning in the 90s may be sensitive to how you quantify it, and may not be robust across different metrics. Some measures find a trend. Others, applied to the same atmosphere, don't. That's not a scandal. That's just what it looks like when you try to put a number on something that isn't naturally a number. But it means a lot of the argument has been people talking past each other with different rulers, and then there's the finding that I think should be more famous than it is. Almost all of this research looks at the satellite era, 1979 to now. That's the period with good data, so that's the period everyone studies, and it happens to be the period when Arctic amplification emerged, which is convenient for spotting a relationship and terrible for knowing whether it's special. So a study in AGU Advances went further back, and found that the 1990 to 2010 rise in waviness, the one that started this whole thing, had frequent precedent earlier in the 20th century. The polar jet was also wavier in the 1940s, and the 1960s, and the 1980s, before the modern Arctic melt, before any of it. So the signal everyone built a hypothesis on might just be the jet doing what the jet has always done, on a timescale longer than our good data, and we happen to be watching during one of the wavy bits. Climate model experiments meanwhile indicate that increased waviness isn't an expected forced response either to declining sea ice or to Arctic amplification. Multiple groups, multiple approaches, same answer. Though I should say there's a third camp in this that doesn't get enough airtime, coming out of Kumu's group and others, and their angle is different again. They're less interested in whether the waves are bigger, and more interested in whether the waves are resonating, whether under certain summer conditions the Northern Hemisphere gets into a state where particular wavelengths get trapped and amplified between latitude bands, like a standing wave on a plucked string, locking a pattern in place for weeks, is a different mechanism, a different season, and a different set of evidence, and it's contested too. But it's a reminder that is the jet changing isn't one question with one answer. It's several questions in different seasons with different physics, and the field is at different stages of confidence on each of them, which is worth saying because the science is unsettled gets used as a rhetorical crowbar constantly. And that's not what I mean. I mean it in the boring literal sense. There are named researchers, publishing in first-ranked journals, who disagree with each other in print right now, and none of them are cranks. Why does the argument actually matter, though, beyond the pleasure of watching clever people scrap? It matters because of what you plan for. If the thermodynamic story is the whole story, then the future looks like the present with the dial turned up. Hotter heat waves, wetter downpours, worse droughts, all of it broadly extrapolatable. Unpleasant, expensive, and forecastable. If the circulation story is also true, then the future contains something else. Patterns that persist longer than anything in the record, in places the record says shouldn't get them, and you can't extrapolate your way to that. It's not the dial turning up, it's the dial turning into a different dial. Those two futures need different reservoirs, different grids, different insurance. So the argument isn't academic, even though it's being conducted in exactly the places academic arguments get conducted. Right. Now the bit that matters most, and I'm going to say it once, clearly, and then leave it alone. None of this means climate change isn't making extreme weather worse. That is a completely different claim, resting on completely different evidence, and it is not in dispute. Blackport and Screen say so themselves, right there in their own paper. Rising global temperatures are expected to increase the severity of certain types of extremes, heat waves, droughts, and floods, primarily for well-established thermodynamical reasons. Thermodynamical, that's the word. It means because the air is warmer. Warmer air holds more water vapour, so when it rains, there's more to rain. Warmer baseline means a heat wave starts from a higher floor, so the same weather pattern produces a hotter outcome. Drier soils in a warmer world dry out faster, so droughts bite sooner. None of that requires the jet stream to have changed one bit. It's the atmosphere having more energy and more moisture in it, full stop, and it's about as settled as anything in the field. This is also, incidentally, why attribution studies work the way they do, and why I flagged Master's comment earlier as an attribution rather than a claim. When a scientist says a heat wave couldn't have happened without human-caused warming, they're not asserting that we caused the weather pattern. They're usually saying something narrower and much more defensible. Run the models with the observed warming, run them without, and count how often you get a day that hot in each. If it shows up in one and essentially never in the other, you've got your answer, and the answer doesn't require anyone to have an opinion about the jet stream at all. The pattern might have happened anyway. The pattern plus a warmer starting point is what produced the number. That distinction gets lost constantly, and it's why the same person can say, this heat was impossible without climate change, and we don't know if the circulation is changing in the same breath without contradicting themselves even slightly. So the argument is not about whether the atmosphere is changing, it's about whether the circulation is changing. And I think that's the single most flattened point in this entire subject, and the flattening is worse than useless, because it hands people a fight they don't need to have. The jet stream is broken is a claim scientists have spent 14 years arguing about and still haven't resolved. Meanwhile, the thermodynamics, the boring, unsexy, no thumbnail potential thermodynamics, quietly did most of the damage while everyone was watching the jet stream. The wavy jet is the interesting suspect. The warm air is the one that actually did it. So when I tell you what the models say about the next 6 months, hold that in mind, because the confident bit and the contested bit are not the same bit, and pretending otherwise is how you end up with a title like this one, Reservoirs. That's where I want to start, because that's where this actually lands, and it's not where anyone looks. A reservoir is a bet. Somebody, decades ago, looked at a rainfall record and sized a thing. They said, over the last 60 years, this catchment delivers roughly this much water, with roughly this much variation, so we'll build for that, with a margin. And then they poured the concrete, and the concrete is still there, holding that bet. Same with a railway. Rails are steel, steel expands, and expansion buckles track. So you install the rail at a specific stress-free temperature, chosen for the climate the line runs through, with a corridor either side of it. That corridor is a bet too. Same with a grid. Same with a road surface. Same with drainage size to a 100-year storm, where the 100 years came from a record that ended before most of us were born. All of it, everywhere, calibrated to a range. And the whole question of what happens next is really just, does the range still hold? And what's interesting about that is that infrastructure doesn't fail gradually. It sits well within tolerance, doing fine for years, and then one afternoon it's outside tolerance and it fails completely. There's no middle. A rail that's fine at 40 degrees and fine at 42 doesn't get slightly buckled at 45. It's fine, and then it isn't, and then there are no trains. Same with a grid. Demand rises with heat, because air conditioning, and supply falls with heat, because transformers derate and transmission lines sag, and thermal plants lose efficiency when their cooling water is warm. So the two curves move in opposite directions at exactly the same time, and they cross somewhere, and where they cross is a number somebody chose decades ago. Which is why the July detail I mentioned earlier, the transit delays, the hundreds of thousands of homes without power, is the part I'd point at, rather than the temperature records. The records are the headline, the grid is the consequence. And the grid didn't fail because the heat was unprecedented in some abstract sense. It failed because it was calibrated for a range, and the range was calibrated in a different decade. So let's talk about what about to actually means, because it doesn't mean prophecy. It means a probability distribution has shifted, and I want to hand you the actual numbers with the actual names attached, rather than a feeling. Start with the caution, from the people who'd most benefit from hyping it. The Super El Niño label is shorthand. It's not an operational category. NOAA has thresholds, and very strong is one of them, and super is a thing headline writers say. It's useful shorthand and it's not a measurement. Now, the substance. Daniel Swain has been making a point I find genuinely clarifying, which is that the big El Niños we've had, 1982, 1997, 2015, produced very different global effects from each other, not variations on a theme, different. In 1983, some Peruvian rivers carried 1,000 times their normal flow. In 2015, you got severe drought in Ethiopia. Same phenomenon, same category, wildly different outcomes on the ground, 1,000 times normal flow. I had to read that twice. That's not a flood, that's a river deciding to be a different river. Swain's also raised something I'd never thought about, which is sea level. A strong El Niño produces a temporary sea level rise of around 6 inches along the California coast. Warm water expands and the wind patterns pile it against the coast. Temporary, it goes away afterwards. But you have to add that 6 inches to the sea level rise that's already happened, which along California ranges from about 6 inches to a foot over the past century, depending where you're standing. And then you have to add the tide, and then you have to add the storm. So a coastal town that's fine normally, with a big winter storm at high tide, gets a winter with an extra 6 inches on the baseline. Nothing about the town changed. The reference level moved. That's the sort of compounding nobody's built for, because each individual component is manageable on its own. Then there's James Hansen, who published in April with a paper titled, and I promise I'm not editorializing, this is the actual title, Super Duper El Niño, which from the man who testified to Congress about climate change in 1988 is quite a swerve. His argument is that even a moderately strong El Niño in 2026 produces record global temperatures because the background warming has accelerated underneath it. He projects global temperature could reach 1.7 degrees above pre-industrial by 2027. And I want to be precise about the status of that. That's one scientist's projection in one paper by a man with an exceptional track record and a well-known tendency to sit at the aggressive end of the range. It's not a consensus figure. It's not an institutional forecast. It's a serious person making a serious argument that other serious people will now argue with. Treat it as exactly that, right? The regional picture, and this is the part I think people get wrong most often, because they assume big El Niño means big everything everywhere. It doesn't. It means winners and losers, and the losers are specific. The Pacific Northwest should be cautious with this setup. El Niño winters in Washington, Oregon and Idaho tend to run warmer and drier, higher freezing levels, more rain at marginal elevations, less total precipitation, and a shorter accumulation season. The northern Rockies carry a similar concern. The high volcanoes and the colder interior can still produce, but the baseline signal is worse than a La Niña winter. So the Cascades potentially have a bad one. Not dramatic, just thin. California is the opposite, and it's the interesting case, because California has the biggest upside in this pattern and the biggest impact risk, and those are the same fact. The Sierra can stack enormous snow totals when the storm temperatures cooperate. Genuinely enormous. But warm atmospheric rivers punch the rain line too high, and then instead of adding to the snowpack you're raining onto it, which chews into what's already there. So the same storm sequence either builds you a fantastic year or takes the year you had and washes it downhill, and which one you get depends on a couple of degrees. A favourable precipitation outlook can produce disappointing skiing when the moisture arrives as rain, which is a very civilised way of describing something that also determines whether the state has water in August. And down on the central coast, one forecast walked through what strong El Niño events have historically delivered, 150 to 200% of normal rainfall. In practical terms, around Santa Barbara that's the difference between the usual 14 inches and something in the range of 40 to 50. Around San Luis Obispo you're talking about the usual 23 or 24 inches going the same direction. 40 to 50 inches is not a wet winter, that's a different climate for a year. Then there's the paradox, and this is the one I think is genuinely underappreciated. Wet winters in the west grow vegetation, grass, brush, the fast stuff, and then summer arrives, and the drought comes back because the drought always comes back, and all that vegetation dries out. And now you've got fuel, more of it than you'd have had if the winter had been dry. So a good winter buys you a bad fire season 18 months later. The rain that saves the reservoir plants the fire, and there's no version of that where you get to choose, because you can't have the water without the grass. The National Interagency Fire Center and NOAA have been tracking high wildfire risk in the southern high plains and the southwest through spring, expanding into southern Utah and the Colorado West Slope by June. And that's against a backdrop where Washington state has declared statewide drought emergencies 4 years running, with snowpack around half of normal and melting early, 4 consecutive years. That's not an event anymore, that's a condition. There's one more layer of caution I want to add, and it's the one I'd want if I lived there. Everything in the regional picture above rests on analogues. What did the last few big ones do? 1982, 1997, 2015. Go and look at what happened, average it up, and that's your expectation. The problem with analogues is that there are 5 of them. 5 very strong events since 1950. That's not a data set. That's an anecdote with a standard deviation. And Swain's point cuts straight through it. Those 5 produced wildly different global effects from each other, so averaging them tells you about the middle of a distribution that has almost nothing in it. And the second problem is that the background has moved. 1982's atmosphere and 2026's atmosphere are not the same atmosphere. There's more heat in it and more water vapour in it, so even a perfect repeat of the 1982 circulation pattern would produce a different outcome on the ground, because the pattern is the same but the material it's working with isn't. Which is more or less Hansen's argument, come to think of it, arrived at from the other direction. So let me actually answer the title, because I think it deserves an answer rather than a shrug. Nothing is about to be unleashed. That's not me being deflationary for the sake of it. It's that the framing is wrong in a way that makes the real situation harder to see. There is no single thing, coiled, waiting. There's an ocean that's warmed up, and a set of probabilities that have shifted as a result, and a large body of infrastructure calibrated to a range that was worked out when the probabilities were different. What forecasters are actually watching is a set of numbers. 97% chance it persists into spring. 81% it goes very strong. Those are strong numbers. They're also precisely odds. And the Climate Prediction Centre already told us what odds mean. And I'm going to use my second and last go at that sentence now, because it's the best sentence anyone's written about this whole subject. Stronger events do not ensure strong impacts. They can only make certain impacts more likely, likelier, not certain. That's the whole thing. That's what about to means when you actually pin it down. Not a prediction, a stacked deck. The stacking is real. Everything else is still being dealt. I keep coming back to the balloon. Not as a nice way to finish. I mean, I actually keep thinking about it, because the thing that carried it is still there. The current Arakawa calculated in 1943, using data a man collected through a telescope in 1924, running strongest from November to March, at speeds approaching 200 miles an hour. That's not a historical fact. That's a description of the sky above North America right now, tonight, unchanged in its essentials, doing precisely what it has always done. It's 8 miles up, it's a few hundred miles wide, it's over somebody's house at this exact moment, and they have no idea, in exactly the same way that nobody in 1944 had any idea, and it doesn't care either way. We found it by accident, twice. Once by a man nobody read, and once by pilots whose bombs wouldn't land. We've spent 80 years measuring it with balloons we throw away and never get back. And we're currently having a 14-year argument about whether it's changed, using rulers we can't agree on, over a period of record that might just be too short to tell. Meanwhile, it keeps going east. Overshoot correct, overshoot correct. I think that's the bit that stays with me. Not the alarm, not the records, not the numbers, just that there's a thread up there, wrapped around the whole planet that decides an enormous amount about the lives of several billion people, and it was doing all of that for the entire history of our species before any of us noticed it was there. Anyway, there's a lot more in this. The ensembles, the stratosphere, the way an atmospheric river actually forms, and I've got half a mind to do a whole thing on Rossby, who deserves more than the 2 mentions I gave him tonight. Another time,